Hello and welcome to the next lecture on the module on VLSI testing. So at present we are discussing on the optimization techniques for ATPGs, which is on basically lecture 3 and 4. So basically this is topic on which we are considering both optimization on techniques for ATPG as well as we are also trying to study the design for testability. So in the last few lectures, on the next lecture on the module on VLSI testing. So in this lecture we will be mainly looking at optimization techniques for design for testability. So throughout this module on VLSI testing, you might have been observed that we have first discussed basically what are the different ways to generate test patterns. That is the basic idea of testing digital circuits, and then we are trying to optimize it so that we can handle larger circuits. But in all the lectures, like when you have talked about scan chain, so you have to find, or when you have to say that we have to put some kind of a compaction circuit, when you are optimizing ATPGs, when you are optimizing based on the terms of test patterns which are generated. So you are trying to merge them or we are trying to compress them, and the outputs we are trying to compact techniques we are using for the output generation, so that actually the number of pins which is required for the AT is reduced and so forth. So different type of techniques we were looking at so that we can try to handle large circuits and we can do efficient testing on them. But on that case we have seen there are two basic issues, that one way you are trying to generate good quality test patterns so that they can handle very large circuits as well as they can test more than different type of faults and so forth. But along with that, you should also observe that sometimes we were putting some extra kind of circuitry for testing itself on the device or all your VLSI circuits. So that is for help in testing we are putting additional circuits. For example, very important is your scan chain. So in this scan chain, basically with the normal flip flops we are putting a multiplexer. For test pattern compression, basically we have a compression circuit and also have a compaction circuit at the output. So additional circuitry what we put is basically called the design for testability. So in this lecture, basically we will try to see how we can optimize the amount of additional circuits we are going to put for design for testability. For example, if I say that to make a circuit testable, basically we can put lot of circuits and lot of additional circuits so that test becomes very easy. But then adding too much circuit will also lead to two type of problems. One is the circuit cost will rise, power will rise, and at the same time who will test the circuit which is you have put for design for testability. If I have a smaller circuit for design for testability, then there is we can assume that as the circuit is quite small, the probability of happening of faults in them can be less, or it will be easier to test the circuit under design for testable circuit itself. In other words, you are putting a DFT circuit to help to test your original circuit, but who will test the DFT circuit? If the circuit is small, still you can do some kind of testing or assume that the number of faults there will be smaller in number. But if that circuit itself is quite large in nature, then that will not serve the purpose. So therefore this lecture is basically DFT based optimization, that what are the optimizations we can do on the DFT circuit itself. That is the key role, that is one of the key challenge we have. Like for example, I can have, instead of having one very long scan chain, I can partition it into 1000 different scan chains. So scan loading will be faster, but then 1000 extra pinouts has to be brought out for all the scan chains. So this way we are thinking how to have a trade off so that we can have a quite logically simplistic DFT circuit as well as your testing remains easier, and that is you are not pushing too much pressure on the DFT circuitry as well at the same time you are not making the testing of the circuit too difficult. So we are coming into a balance. So there are basically, if you look, there are two ways of handling DFT. One is called circuit dependent. So for a very different particular type of circuits, you can put different type of inbuilt circuitry to enable them to do the testing. So it may depend on the functionality of the circuit. So that is actually a totally design problem. We are not going to highlight on this. That is, given a circuit, given the functionality, I want to put some kind of maybe say some kind of special test pattern generator inside the chips which can help you to test it. So but it will be very much dependent on the circuit functionality or the type of circuit being under test. So for that it is totally based on design to design and a case to case basis. So there is no algorithm as such, or I can say there is no generalized architecture to do this. So it has to be handled in a case to case basis by the designer and the test engineer targeting that particular design. So as this is not a very generalized way of handling those things, so we are not going to look at the circuit dependent part, rather we are going to look at the circuit independent part of DFT optimization. So what are the optimization of scan chains? So if you have looked at the circuits under test, so we have seen one of the most important DFT circuitry is the scan chain. So for every flip flop we make it scan enabled so that you can make a chain out of it, so that you can very easily load the test patterns in sequential circuits and get the response out of it. So first we will see what are the different ways of optimization of the scan chain. So in this lecture mainly we will be focusing on this, that how to optimize scan chains, because that is one of the most, or say that the 99.9% area of your DFT circuit is taken by the scan chain itself. So we will try to see basically how do you can optimize scan business so that we can load the scan chains faster, as well as you do not put too much overheads in terms of the size of scan circuitry, because scan circuitry means you are putting some flip flops, as well as there should not be more pinouts. Other optimizations are basically compression circuit, decompression circuit, convection circuit, etc. So that is another way that how can you compress the ATP test pattern, so that your compaction, decompaction, all those additional circuits you put in, which are actually helping in compressing the circuits and compacting the output response, also does not become too large. But that is again, I mean, that is also a lot of work has been done in this area also, but that is more related to some kind of coding theory, etc. So in this lecture we are not going to highlight mainly on that, mainly we will be looking at the scan chain. As I told you, the relevance that almost there is no circuit at present which can be built without a scan chain. So most test engineers emphasize on optimization of the scans. Right. So we will while we will go through these lectures, you will be automatically motivated, and you will automatically be able to find out that why scan chain optimization is so important, because scan chains is not only about the flip flops which you put additionally, but also about the pinouts. One extra scan chain you put, one additional pinout has to be there. So therefore optimization of the scan chain has a greater role to play in optimization compared to other cases like compaction circuit and decompression circuits, etc. So first let us look at some definitions. So first, something is called sequential depth of a flip flop. So sequential depth of a flip flop implies that, so if there is a flip flop and there is a combinational circuit, so and this is the primary input. So how many D flip flops are there in the path between the primary input and this flip flop? In other words, there is a flip flop like this, there is some combinational circuit and there is a primary input. Is there any flip flop in between this flip flop and the primary input? If there is none, so this will be level of 1. Now again, if I zoom here, you will see there is another flip flop and another combinational circuit, and the primary input is here. So basically between the second flip flop and the primary input, there is one flip flop in between in the path. So therefore level depth is actually 2. So what it says, if the output of a flip flop can be controlled by only primary input, there is a sequential depth of 1. It implies that only primary input and a clock. So therefore no flip flops in between. So that is level 1. And if one flip flop come in the path, level 2, and you keep on doing. Now what is the importance of level? Because the flip flops of level 1 can be controlled just by the primary inputs, assuming that there is no scan or set reset lines. Of level 2, how can you control? You have to control the primary inputs, as well as you have to also control the flip flops on depth 1. So to control a flip flop at level 2 depth, you have to control the primary inputs, as well as you have to also have a controlling value of all flip flops at level 1. All implies whichever is lying in that path. So therefore that is called the idea of the depth of a flip flop. Next definition, just to keep these things in mind, so that we will be using it to understand that what is the difficulty of testing a circuit or a flip flop if the depth is at a higher level. So of course, if all the flip flops are the level of depth 1, then all the primary inputs can be used to control that flip flop. Of course, if some of the flip flops are a very higher level depth, then first you have to do control level 1, then you have to do control level 2, level 3, so forth, so that finally the flip flop at the jth level can be controlled. So more the depth of a circuit, more difficult is to control those flops to get a proper testing done. So this is a non-cyclic circuit. One very important thing, that is a cyclic flip flop. So that means what? The input of this flip flop again depends on the output. So between a sequential circuit is non-cyclic if there is no flip flop whose input is dependent on its output. Therefore, that is this output is dependent on its input itself. If such a flip flop is there, this may not be controlled. Means there are many cases they can be controlled, but there is a possibility that if there is a flip flop which is cyclic, it may not be controllable. But the other story is, if the circuit is free of cyclism, that if no flip flop in a circuit is cyclic, or the cyclists or all the flip flops are non-cyclic, then they are always controllable. Maybe there is some flip flop at 1000 level depth. You may require 10,000 depth, so 9999 clock pulses may be required, and all the flip flops from level 1 to 9999 level has to be controlled to control the final flip flop whose depth is level 10,000. But you will be able to do it. That is guaranteed. Of course, we have seen that basic idea in this result. That first you control this one will control level 1, then again you use the primary outputs, this is already controllable, so you can control this one, and in an inductive manner you can do it. But if there is a cyclic flip flop somewhere, then that flip flop may not be controllable. So there is only way to control such flip flops is either by scan or by set reset. So that is the basic idea. So there is a property which says that the secondary inputs of a cycle free sequential circuit of depth D sequence, secondary input means the output of the flip flops, basically something like that. So if you see, so if I look at here, let me erase this. So, secondary input means it is something like, say the output is actually feeding the combinational circuit. So, these sometimes people call it as secondary inputs. The output of the flip flops are called secondary inputs. So, what it says, the secondary inputs of a cycle free sequential circuit of the DSQ can be brought to controllable value in at most D sequence input patterns and clock pulses. That is how basically if some flip flop is there at D sequence level, so its output can be controlled, then you have to control all other flip flops which are at the level D sequence minus 1. So, you require D sequence minus 1 plus 1 patterns to actually control that flip flop. That is something like first you control at the primary inputs, then you control level 1, level 2 and keep on doing it. So, you reach the level D sequence. So, that is quite obvious, I have shown you from the figure. So, and the proof is also given, the proof is basically obvious. All flip flops with D sequence 1 can be controlled by setting the primary inputs and a clock pulse. Now, level 2 can be controlled by D sequence 1 being controllable and the primary inputs. You keep on doing it and then basically you are going to see that D sequence number of primary inputs are required and clock pulses to control a flip flops at the level D sequence. Right. So, basically the simple idea is in a block diagram we can say that this is a flip flop of level 1, this is flip flop at level 2 and this is a flip flop at level D sequence. So, okay. So, this one can be controlled in one pattern of primary inputs and a clock. This one will require 1 plus 1 because one pattern set will be required to control this flip flop and then another primary set will be going to do it because this is something the output of this is feeding to this flip flop and you have to keep on doing it inductively so that you require D sequence. So, any flip flop at the level D sequence can always be controllable by the test patterns whose number is equal to D sequence. Now, number of patterns will be maximum required D sequence and clock pulse has to be applied for each pattern because flip flops keep on moving the data on clock edges. So, that is what is the idea. So, what it says in a very layman's language that if there is a system or a circuit with flip flops whose level is say k and there is no cyclic business. So, in cyclic flops then they can always be controllable. So, all the test patterns can be generated and all the test patterns can be put into that circuit and all faults can be tested, but it will take time. So, if for example, the circuit has some flip flops with 20,000, 30,000, 40,000 levels, then what you will do? Basically, you have to keep on pumping the values and everything will take some 10,000 or 20,000 time, right, because some flip flop at the level of 10,000. So, that means 10,000 primary patterns has to be applied at 10,000 different clock pulses. So, it will keep on, first it will set flip flop level 1, level 2, level 3 and keep on doing it. So, lot of time will be required to pump in the values. So, and that is there. So, now if you say that what if I use a scan chain? Scan chain will solve your problem, but still the time taken will be very, very high. Right, I will just give you a very simplest example, will actually I will try to make it. Scan chain actually solves the problem in a very indirect manner. The idea is that, so as I told you, there is two ways of optimization. If you have seen my lectures on ATPG in this module, so two things, how difficult is to generate the test patterns and how difficult is to apply it. Scan chain do not actually help in reducing the test application time. It only reduces the test pattern generation time, but it is a secondary factor because test patterns are generated only for once at the soft level and they have to be applied at all the circuits. So, test pattern application time is very, very important compared to test pattern generation time. But on the other hand, still if your circuit is very, very large, you would also like to optimize at the level of test pattern generation also. How? As we have already discussed, scan chain basically will tell you this point maybe I want 1, this point maybe I require 0 and so forth. Scan chain will directly tell you that I can do it. You need not put any kind of mathematics or backtracking or sensitize, propagate and justify to find out what are the values here. Because if you remember, if I do not have a scan chain, then if I want say for example 1 here, then you have to calculate on what values I have to give at the primary input so that I can get a 1. Then again what I have to do here so that I get a 1. So, lot of sensitize, propagate, justify. So, all this graph theory traversal has to be done to find out how I can make 1 using this circuit which actually controls it. But if you are using a scan chain, so I can directly make it as a 1 in a chain. So, test pattern generation time did not do any kind of backtrack etc. Directly it can say that okay, directly I can make this pattern as 1. So, test pattern generation time is highly optimized if you are using a scan chain, but test application time is not solved because if there is a scan chain whose length is say 10,000, that means basically if you, for example, I can say quote unquote if some of the flip flops are in the depth of level 1000, so the scan chain length also will be 1000 because that means this last flip flop is dependent on from primary input to the primary output of this primary, sorry, there is a flip flop say whose depth is 1000. That means if you take a path to the primary inputs, then there will be 9999 flip flops which will be in the path. So, if you make a scan chain, the scan chain length also will be of the level of say will be 10,000 and also you will require 10,000 clock pulses to feed it. So, scan chain basically does not save your test application time. It only helps to generate test patterns quite faster, because you need not do all kind of backtracking that what values will be required to put this value at 1 and what at this gate what values will be required, because flip flop will be directly controllable. So therefore, now we will try to see that what we can. So actually just a minute, this time frame testing. So whatever where we are saying that without use of scan chain, still you can test a circuit if there is no cycles. So therefore you have to calculate what will be the value, then we will have to check for the primary input value so that the values can be propagated to the flip flops and so forth. That is sensitizing and justifying and all this. If I do, the term is called time frame expansion approach, because the 100 flip flop or the 10,000 flip flop will be set at the 10,000 clock pulse or the 10,000th time. But before that, all the time frames has to be set up from 0 to 9999 so that the final test pattern can be applied at the 10,000th iteration. So the term is called time frame based expansion, and the other one we know is the scan chain based. So time frame based expansion actually takes lot of time for test pattern generation, but test pattern application time is same for both scan as well as your normal circuit without a scan where there is no cycles. The idea is very simple. So in scan also, if there is a flip flop, if there is a circuit with level 10,000 depth, the scan length will be 10,000, as well as the normal circuit without a scan also will be having some flip flops at the level of depth 10,000. So you require test patterns and clock 10,000 clock pulses to set it, and in case of scan also it is the same story around the line. So generally quote unquote saying that test scan chains may not be directly helping you to solve the test pattern application time. It only generally helps to solve or minimize the time required to generate the test patterns. Well, now let us take some examples. So this is a circuit as you can see, and we have a fault at the output, this one. So now there is no scan, there is no flip flops, no scan. So we are assuming that there is no scan chain over here. So how do you do the test pattern generation? By the time frame expansion method. Generally what we do, we first actually replace these flip flops with some dash. We assume that the lines are continuous. Then we will go for a ATPG. So what will be the ATPG here? Stuck at 0. So you have to apply a 1 normal case and fault it is 0. So that is what basically normal 1 for the sensitization. That is going to give you the value of D over here. Then I have propagate the value of at the output, so I am propagating it. So sensitization is done, propagation is done. Now if I as a D is the OR gate, I am justifying. So D is the OR gate, so I will have a 0 over here, this one, NOT gate 1. Of course, this is a AND gate, so I require both 1 1 here. So I will require a 1 over here. So anyway, this is a 1, the 1 required. Fortunately, there is no conflict. So I come over here. So I require this again the output of this AND gate E equal to 1. So I will be requiring a 1 over here, 1 over here, and your job is done. So basically, this is the case. So this is what is required to test it. Now, what it says that this flip flop, this output also has to be a 1 and this has to be a 1. So I am doing the ATPG. Now you see, this is done. The ATPG is done. So if this scan flip flop, non-scan flip flop, this ATPG has to be done. So now what it says that the output of the flip flop, this has to be a 1 and this has to be a 1. So if it's a scan chain, what we will do? We will do nothing. We will just say this will, there is a scan business, so you can directly set them to 1 1. So your ATPG is done. But if this scan is not there, then what you have to do? Then I have to think that how can I make D equal to 1 and how can I make I equal to 1? That has to be done in 2 time steps, because this flip flop is at level 2 and this flip flop is at level 1. So you have to apply this the values of 1 1 to these flip flops in 2 time steps. In scan also there will be 2 time steps required to do it. Without scan also it will be 2 time steps. But in case of scan chain, you do not do any computation after finding these values and these values. You can directly apply them because they are scan. But if in case there is no scan, then you have to again do some kind of computation to find out how can I make 1 over here and how can I make 1 over here, and do it. We will show you. Now first thing is that we have to make 1. You have to apply 1. How can you do? Scan business, don't worry, ATPG is done. But here ATPG will actually do some kind of extra steps which is called time frame expansion. So it says I require a 1 over here. So you have to make C equal to 1 and you have to apply a clock pulse. So that is the first time step you have to do, or you can, first time step you have to do this. So there is extra computation at the level of computation of ATPG only. This has nothing to do with application. So when somebody has told me that D equal to 1 and I equal to 1 is to be there and there is no scan business over here, then ATPG tool will again do something extra. It will say that you have to apply C equal to 1 and then you have to apply clock pulse, you will get a 1 over here. At the time these are XX. Done. Now you know I have a 1 over here. One time step has been done. Now I require a 1 over here. How can I do that? For that basically also I will be requiring what I require. I know I have 1 has to be there. I require this one is required over here. So what I have to do, and also you have to remember that next stage also it has to be a 1. So what I have to do, 1 has to come from here, this 1 will be used to set it, this is required. So this 1 will be helping to set it, and but when this 1 will go away from here, I also still require D to be a 1, because final testing I require D has to be a 1. So what I will do, again I will put a 1 over here, in the second time step I will require a 1 over here. So assume, you have to understand that some ATPG tool is telling you, because you will be applying it, but some the ATPG tool is actually telling you what to do when. So first it has told you that basically you have to apply a 1 and you have to apply a clock, so 1 it will be there. Next what it will tell you, you put a 1 over here, apply a clock pulse, also you have to put B equal to 1, A can be X at this time. Why? Because this 1 and 1 you apply, because this is 1, already 1 has been set, you apply this 1 at the second time step, these are 1 AND gate, then you again apply a clock pulse, this 1 will be actually reflected over here and this 1 will be replacing at the 1 at the second time step. So you can see lot of extra computation is being done, which is telling you that first stage you apply XX1, ATPG is telling you, next stage you apply 1 1 and a second clock pulse, then basically you will be having a condition of, so 3 stage ATPG it has become. First step basically it will tell you what to apply. Had it been a scan chain business, no more ATPG has to do anything, automatic test pattern generation will say the scan is there, directly you set this flip flop as 1 and you do it. But we are assuming that at present there is no scan chain, so you have 2 more extra steps the ATPG is telling you, that first you have to do this and second time step you have to do it, and once it is done you are going to have this value, then you will be able to test this circuit. Now what I have to put over here? I have to put a 1 over here, so 1 1 is 1, so the answer is D. Now propagation already we know D, this is 0, already we know that is a 1, so it has been done, and B also has to be a 1 because I require D has to be 1. So if you look at, now what? Now you look, there are 3 patterns which has to be applied. So I am zooming it out, so that this is the final pattern which will test your circuit. So first pattern is this one, AX, BX, C1, second stage is AX, B1, C1 clock pulse, and this is the final one, A1, B1, C I don't require, and your circuit will be tested. In fact, this is the only test pattern which is required to test your circuit basically, which will be done if you are having a circuit without with a scan. So if you just take this raw circuit, run for ATPG, it will give you some pattern, and that is a single pattern will be told by the ATPG. So your job is done assuming as a scan is there. If you are not assuming a scan, so 2 more extra computation has to be done. Again I am saying our quote unquote computation has been done, which will tell you what to apply. So finally the ATPG is a 3-step ATPG in this case. So first pattern, second pattern and third pattern. So this ATPG is going to tell you and you have to do it. So what you will do? First you will take your circuit and the test. Now we are saying test application. Now I am changing the mode. So this your tool has, ATPG tool has told you that these are the patterns to be applied, computed. So with scan only one computation is required, because we know that very easily I can set this flip flop and don't require any computation for that. But now no flip flop is scan enabled, so 2 more test pattern part it has told, because there is no scan, so it is called time frame expansion method. So it has told me, so first I have to put AX, then I have to apply a 1, then next stage I have to have stage 1, next stage again it is an X, but next stage it's an X, I have to put a 1 1 and a clock pulse, and third stage I have to put 1 1 and I don't require it. So 3 patterns I have to put and my test will be done. So this is application, but what to apply basically is computation. So it's a 3-part computation has been done by ATPG tool, and it has told me that these patterns has to be applied. Now I am applying. So one thing I think is very clear to you at present, that if there is a scan chain, so I do not require a 3-stage ATPG to do it. So you have to appreciate the fact that if there are 10,000 flip flops in the dependency list, or the depth is 10,000, so this scan, so the ATPG will also have a 10,000 step ATPG in the worst case. So it will be ATPG, test pattern generation will be very, very complicated. But once say I have done that ATPG, it has told me that these 3 patterns are required. Now I have to apply it. So I am applying first this, second this, and this, and your job is tested. Now again, assuming that there is a scan, so how will you scan it? So I have to put a 1 over here, I have to put a 1 over here, and then I have to put some 1 1 or some value to test it. So scan chain will also take 2 time steps. First I have to set this, and then I have to set this. So test pattern application time is same both for scan as well as for a normal mode of circuit, because I have to set these 2 flops to 1 1 to make the values requirement of 2 able to test it. So from this example it is clear that time to test this circuit using scan is same as the one without a scan. because in this case these 2 flip-flops are there, I have to set it. This also requires 2 clock edges, and in case of without a scan also I just require 3 patterns to do it. So scan chain basically, as I have illustrated in the example, is not that way saving your test application time, only it is saving your test pattern generation time, because in this case these 2 extra time frame patterns has to be generated, which is actually not good. So if you have a very big circuit, you will have some 10,000 flip-flops in your line, so test pattern generation also will kill you. Now important question arises. So if your scan chain is not saving time for test application, because as I told you, test pattern generation optimization is also important, but time of test pattern application is more important. Why? Why more important? Because test pattern has to be generated only once, but test pattern application has to be done for all circuits. So it is very, very important to think how can we reduce the time to apply test patterns to all the circuits, how the test pattern number has to be reduced. Anyway, that already we have seen in test pattern compaction, etc. We are not going into right now. So now the question is, if the test pattern application time is not saved by the flip-flops, then can we do something? Because anyway test patterns are basically, scan chains are taking more area over it because of your flops. So what can I do something like this? Some of the flip-flops actually I will make scan enable, of course, which are very down the depth in line, because you will require a lot of ATPG computation to find out, because as you have seen here, so the level of this flip-flop depth is 2, so 2 extra test patterns were required. So can I do something like some of the flip-flops which are very down the line in depth, so those I will put scan. But some of the flip-flops which are very easy, like this one, I really do not require any computation. It's a primary input directly connected. To get a 1, I just require a 1. So ATPG, to find out how I can get a 1 is very, very straightforward. So ATPG will not take much time to generate that. But say there is a flip-flop very long down the line and I want to have a 1 in this. So the test pattern generation tool will take a lot of time to tell you how I can get a 1 in this flip-flop and what are the values to be set down the line. So such distant flip-flops or difficult flip-flops can be scan enabled. But such flip-flops which are very near to the primary inputs, which can be very easily directly controllable, and the test pattern to be applied does not matter much, we can eliminate such flip-flops from the scan enable. That means flip-flops which are very down the line will be scan enabled. Flip-flops which are very near to the primary inputs, which can be very easily directly controlled, we will not have any scan in that. So this one will actually make a trade-off. Difficult flops, difficult to be controlled, yes, we will keep scan, because anyway that is going to take some extra pins, as well as you have to appreciate the fact that there will also be a lot of multiplexing arrangements for that. But flip-flops which are very near the primary inputs, very easily can be controlled, we will not connect them to scan. So we will save in the number of pins, as well as we will save in the number of your basically multiplexers addition has to be put. So therefore there is some concept called partial scan chain. So partial scan chain says that difficult to test patterns, difficult flops down the line will be scan enabled, easier ones to be set and reset will not be scan enabled, which will set using a time frame expansion method. That is what is called the concept of partial scan chain, and which we are optimization technique for scan business. So this whatever I have told you in orally is written in this slide. You can read this and find out the textual interpretation of my talk. But I will give you an example. Again, always it is easy to illustrate with example. Some circuit is there, and also of course one thing I forgot, if there are any cyclic points. So if there is a cyclic point, of course that flip-flop has to be scan enabled. So if flip-flops which are very down the line, difficult to control, and also flip-flops which are cyclic, because cyclic flip-flops anyway cannot be controlled by any means. So there you put a scan so that it can be directly controlled. So in this case basically we have taken a circuit and there are flip-flops, these lines are flip-flops, I have not drawn over here. So there are 2 flip-flops. So if you look at this circuit, this is a circuit where there is a cyclic business. The output of this flip-flop is dependent on its input. So these are cyclic flop. So obviously there has to be a scan for this, you cannot save. So this should be a scan flop. But this flip-flop if you see directly connected to the primary input, very easily it can be controlled. So whatever value you require can be directly obtained from this. There is no requirement for any computation to find out the value. Directly you can say whatever is in C will be reflected at T. So do I require a scan for this flip-flop? No. So in a partial scan I will make this as scan enabled and this I will not make as scan enabled. Of course this is a cyclic flop, you have to have a scan, but also there can be a story that this flip-flop is around depth of some 20,000, very difficult to control. So ATPG will also take long time to find out a value to be controllable. So we assume that this is not cyclic scan, but a lot of 10-20,000 gates are there and say that I require a 1. So for the ATPG to calculate, or the ATPG tool to calculate that what I should do, what values I should have here to get a 1 here, it will take long time to compute these values at the inputs. So those flip-flops also I can make scan. So rule of thumb, Flops which are very near the primary inputs do not make scan enable. Flip-flops which are cyclic or down the line in depth make them scan. So that is actually called a partial scan. We will take an example. This example we will now elaborate. So for example, stack at 0 has to be tested over here. So I have to put a 1. So stack at 0. So I have to put a 1 over here. So the answer is D. Propagation will be D. OR gate, the answer will be a 0 over here. Here the answer will be a 1. Right. Then basically this is the AND gate. So all these values has to be a 1 because I require a 1 over here, and basically I require a 1 over here to test it. So A has to be a 1, and of course this flip flop has to be a 1. So basically you require a 1 at this flip flop, you require a 1 at this flip flop. Very simply you do it, you will get the idea. Now basically you see that this is a cyclic flop. I require a I require a 1 over here, and this point basically is 1. This is 1. This is a stack at fault. So now as a cyclic flip flop, I cannot do this control. So what I will do, I will make it as a scan business. So directly I will set it to 1 because whatever value I set over here is again dependent on this. See, I require a 1 over here, and for this line M actually required to be a 1 to make this output as 1. But again this 1 is again dependent on this. Is a loop. Very simple, that this story is a loop on this. So to avoid this loop, so what I will do, I will actually make this F2 as a scan flip flop so that I can directly set it as a 1. So once I directly set it as a 1, so basically, and this is also a 1, A is also 1, this is directly set as 1. So your output is going to be a 1. So now in this case it is a 1, 1, and this has to be a 1. So you will also get a 1, and this 0 can be obtained. So what I will do is that I will make F2 as a scan flop, and this I will not make as a scan flop. So again this one is illustrated over here. So this is actually I have made this as a scan flop. So now I will make it as a scan enable. So you can see over here, I zoom in. So this is a scan flop. So this is scan in, scan out. So I have made this value as a 1. So this scan set has already been done as a 1. Now next stage, this is already a 1 has been set by scan. So you can see this is the scan enable has been done. So this 1 has been set. You can see this output is being decoupled. So this scan has been enabled and this value has been set with a clock pulse. Next, this you can zoom over here and see this scan has been disconnected. So the value is 1 over here, and then you put a C equal to 1 and you apply a clock pulse. So now interestingly, this is enabled by scan and C equal to 1, our D will appear over here. So this part is actually non-scan. This part is there must be a time frame expansion method. So see, even if it would have been a double scan, even if you have made this and this as scan enable, till 2 clock periods would have been required to set this as a 1 and this as a 1. But what I am doing is that I am not setting it as a scan enable, because it is very easy to know that if I require a 1, a C can be set as a 1. So ATPG or tool does not require any complexity. So I do not make F1 as scan enable, and I save something on what do I call your DFT cost, because there is no multiplexer over here, but here there is a multiplexer over here. So next is what that has been done. So already 1 has been set, I put D equal to 1, and now my job is done. So you can just have a look at it. So after that I require A equal to 1, B equal to 1. So if you do that, basically this is 1, so this is also 1, so you are going to get the value 1, and this is a 1 inverted 0, so you are getting a 0 over here, and already you see A equal to 1, so which is going to this gate, and basically I equal to 1 already set by the scan flop. So this is 1 and a 1 is 1, D, and the value is propagated and your job is done. So basically there are 3 steps in this one: set the flip flop FF2 by scan to be 1, set flip flop 2 as scan mode, make it 1, set flip flop 1 as non-scan mode using a time frame expansion approach, C equal to 1, you get D equal to 1, and finally apply the pattern 1 1, and you are going to test this one. Advantage that this pattern, this flop is not scan enabled, so you are saving on the multiplexing cost, and this had to be made scan enabled because it is a cyclic flop. Also F2 could have been a flip flop which is very down the line of depth, some 10,000 to 20,000, then the same approach which we will do. So basically that is what is the idea. That is one way of optimizing the scan chain, which is very popular, is partial scan. Select a set of flip flops which are easy to control, don't make them scan enabled. Select another set of flip flops which are very difficult to control or cyclic, make them scan enabled. So there should be a trade-off. So the trade-off means we are saving in the number of pins as well as we are also saving on the number of ATPG computation time. So this trade-off actually is an optimization criteria. You have to decide that which to be set scan mode, which set to be non-scan mode, and there is an optimization. So that is why flatly saying that all the flip flops to be scan enabled in a very large and a complex circuit, we put lot of extra multiplexers and it will eat up your area. And see, if you say that in a very weak circuit I do not want to put anything in scan, will actually kill you in the test pattern generation time. So there should be a trade-off for optimization. Next problem, again we have told you that scan chain does not help you in reducing the test pattern application time, because if a scan chain has 10,000 flops, 10,000 time clock periods will be required to fill it. How you can optimize it? There is something called parallel scan. So what do you do? So for example, so they say for example there is 2500 is the chain length. Say there is a weak chain of flops whose depth is 2500. To scan it you require 2500 clocks. So what you can do? You make parallel, you cut it. So all the flip flops has been parallelized into 100 different parallel scan chains. So instead of one long scan chain I have partitioned it. So now obviously this 100 parallel chains can be, data can be sent in parallelly. So what you are saving? So instead of 2500 clock pulses to do it, you will just now require, by divide by 100, 25 clock periods you will be able to set up all the flops. Obviously long chain you cut it, you feeding parallelly, so that amount of speed up you will get it. What is the cost you are paying? In the number of input speed. So in one scan chain you would have only 3 pins, scan in, scan out and scan control. Here in this case you will have 200 extra pins, because for each of these scan ins, and sometimes actually somebody put a compaction here, because they just very much interested to load the circuit, output response they compact in and insert it, though they do not exactly talk about scan out, but whatever you do, parallel scan load means at least 100 extra pins you have to require to load them parallelly. So as I already told you many times that having many extra pins loads, these are very difficult to have in a package circuit, as well as that much pin you have to have in your automatic test pattern generator machine. So that is what is the reason of test pattern compression. We have already seen, we try to reduce the test patterns by this width, so that basically number of pins of your automatic test equipment reduces. So again, as I told you, there is a lot of trade off. So for very large circuits or circuits which have a very long scan chain, people try to parallelize. That is, but how much depends on what are the amount of time you will save and what is the extra amount of pin outs you can spare. If you have lot of pin out to spare, you make very large number of parallel scans, so you can load faster, but of course your pin outs will be higher. So that is another way of optimization to find out basically what is the number of extra pins you have and what is the how much speed you require to load it. Of course there is, we do not talk about external pin outs as 100 because of the fact that they do some sort of compaction. Interesting. Something like, say that this is a big scan chain over there, I partition into 1, 2, 3 and 4. I partition. So I require 1, 2, 3, 4 pin outs to do it. But can I reorient or organize the circuit in such a fashion so that I will have a single pin to load all the circuits? Means, can I shuffle out all the scan cells in such a fashion so that, and I partition it in very nice scan chains, may not be of equal length, so that the same values can be given in all the time. Say for example, I have 2 scan flops here, I make a 2 scan lines. For example, I require 1 0 over here and at the same time also require 1 0 over here. Then I can have a single scanning pin, because I have shuffled the scan chains in such a fashion so that here also I require 1 0, here also I require 1 0. Of course it can also be 1x depending. So again compatible vectors are coming into picture. So can I do something like that? Can I reshuffle the scan cells in such a fashion, and can I put the scan cells, can parallelize the scan chain in a fashion in such a way so that same values can go in this? Then what it will help you? It will speed up the application time. Of course the parallelism is there, and you do not require n number of scan pins. Problem is, pin outs is very difficult to handle. More pin outs, very difficult in a package. At the same time AT will have lot of pins. So that is actually called the Illinois scan architecture, which is one of the most founding discovery for scan chain or DFT optimization. That what you do, you try to find out, this is the most generalized goal. There will be a single scan, and internal scan chains I arrange in such a fashion so that the same test values can go in all these scan chains and your job is done. But this is actually a dream which can never be true, because I will give you an example. Say some example, for example, this is some parallelization you have done, this is an AND gate, and same values goes in, because I have only one scan pin, because you always want to reduce the scan pins, because more pin outs, more problem, more ATE pins. But you see, then only I can have 2 patterns that you can apply, all zeros and all ones. Because same input, either the input can be 1 or the input can be 0. So this AND gate can have only 2 test patterns, 1 1 1 and 0 0 0. So many faults will remain untestable. Of course, because as we know, so 1 1 1 will test for all the stacked 0 faults, but 0 0 0 will test only of the few faults. Few test patterns like this and this are actually required to test all other flops. So many other faults which will not be done. Anyway, that you can easily revisit the first lecture on testing and you will find out. So the idea here is that as a single pin, so I can either put 1 1 1 in this gate or 0 0 in this gate, but other patterns will not be able to applicable. So some faults will not be able to be tested. We do not require that situation. We are actually having very less pin, very good. Scan chains are loaded parallelly, but still I do not want to compromise on test. So what I will do? So this is basically your Illinois architecture. So again we will trade off in between. That is called intelligent grouping. That among all these scan chains we will reshuffle as we will make some groups, and in those groups you can at least put the same test patterns. So this is called actually Illinois scan intelligent grouping architecture. So that the number of pins is not, say there are 100 scan chains here, the number of pins will not be 100 and also it will not be 1. 1 is one extreme and 100 is another extreme. We will have something 10 or 12 in between, so that now these scan chains are grouped, so that in each group you can put the same data and no faults will remain non-tested. Right? So that is actually concept of scan compatibility has come. It is very similar concept to test pattern compatibility. That is, two input scan cells are compatible if and only if no faults become untestable as a result of trying the two cells as single input. That is, scan cells are tied and they will always get the same input. So there should not be any fault that is non-testable. Similarly, this cell concept you can also move it to scan chain and you are going to get the same thing. That is, two scan chains are compatible such that if you put, they can always get only the similar pattern, same pattern will go through the scan chain. They cannot have different input patterns, but still no fault should be untested. Then they are actually called compatible. So determination of all possible compatible scan chains are extremely difficult problem. So there are a lot of heuristics to solve it problem. Anyway, that you are free to read it, as I am already telling. This course actually directs towards optimization. So we cannot tell you about all the heuristics how to solve it. They are all available in the research papers. So the idea I think is now clear to you that somehow you have to reshuffle the scan cells. Sometimes you have to make some groups such that scan chains which are compatible are in a single group. So now you will not have as simple as a single pin and take a long time to load the circuit. Also you will not have 100 pin outs, and which is a very infeasible situation, and you are loading all these scan chains parallel. You will have result something in between. Now interestingly we will have nice grouping, so that in those groups at least you can send the scan chain parallelly using a single pin in that group. That is something called what I told you is very similar to compatible patterns or compatible ATPG, which we have already seen in the last lectures, that if two test patterns are compatible, then they can be merged. Similar idea. So basically there are two test vectors like this, and the second vector is this. So you can see, if you look, say example I am partitioning into 5 scan business A, B, C, D and E. So you can always see that A, B and D, E. So they are all compatible chains. You can just see that this is 0, 0 and basically this is also 0x. 0x, 0x, so this is 1, 1, 1, 1. So you can easily see that A, B, D and E are compatible chains. That means I can have a single input for this whole thing, so I can club it as a 1 because there is no conflict. But if you look at C, I think if you look at C, there is a, so in this case no conflict, sorry, in this first case everything is compatible. This is a full compatible chain. So I can connect it. You can see there is no conflicting pattern. So all A, B, C, D can be supplied from a single chain. But here if you look at, in this case if you see A and B, there is no compatibility problem. C and D also there is no compatibility problem. So these two I connect and do it. But only problem with this pin C. So in this case if you see this is 1 and the others are 0. So these are non-compatible pin. So I have to supply scan chain C with a separate pin, and A, B, D and E I can club and I can put data through a single chain, single input. So this is input 1 and this is input 2. But in the first example all these scans are compatible, the single input will actually solve the purpose. So this concept is very similar, that basically now again this is not as simple as that, because always your scan chains may not be of equal length, so slightly up and down all this, there is a lot of trade-offs actually, I am not going to go about it. But how do you exactly select the scan length, how do you partition, whether in 5 or in terms of 6 or 7. So there are a lot of trade-offs to find out that what will be the part, because means one group can have length of 5 and a scan chain length 5, the second group can have scan chain of length 10, the third group can have scan chain of length 200 each. So how exactly you partition, and what is the most optimal way of partitioning, so that the number of pinouts is minimized as well as there is no fault remain untestable, and we can solve this by the compatibility purpose. This is an NP complete, very tough computational problem, and you cannot find an exact algorithm to do it. It will take exponential amount of time. So there are a lot of heuristics to do it. So what are the parameters? How many parallel scan we'll have, how many groups will require, in each group which scan cells will be there, and what will be the length of the scans in each group. So lot of parameters are there. Idea is that you should minimize the scan pins and no faults would remain untestable. This is possible if and only if your inputs to a group are compatible. That is what is the idea. So that is the problem. Lot of heuristics are there, you can read it, but also you can find out the most worst kind of example will be you try all possible combinations. So that is very difficult to solve. Anyway, you should not think about it, but in this slide I think I have tried to give you the idea what is the problem and what the solution would look like. Very simply, you can easily map to a very well known graph coloring problem. So basically you think that A, B, C, D are all these scan groups or scan chains. Basically in this case there are 8 scan chains, there are 8 scan chains. So each scan chain will be basically your node, and I have a point in between A and B. So there is an edge between A and B if they are conflicting. So A and B are conflicting, so I have an edge. So that A and B cannot be supplied patterns by a single pin because they are conflicting patterns. Now you color your graph. So of course if you see that if you have an edge, you cannot have the same color, that means you cannot have a same pin to supply it. You do it with minimum color, and for each color you will have a single pin. Like A and F, they are basically compatible test patterns because there is no edge in between. So you do it, solve with the graph coloring problem, it's an NP complete problem, then you can find out how many minimum colors are required to do it. Along with that you can make a group accordingly. But again, very big circuit, the graph size will be very large, and you also know that graph coloring is an NP complete problem. So a lot of heuristics are there. You can use these heuristics to solve this problem, and then you can find out what is basically your groups, and each group, basically what will be number of groups, and each group will have a single pin, and this optimization problem can be solved. So that is actually called the Illinois scan architecture intelligent groups. So the problem is very simple to design, very simple to map, but solving will take long time because in such case of big circuits the graph itself will be large. So we will follow different type of heuristics to solve the problem. So now, this is about basically your flip-flops, scan chains, partial scan, and of course with Illinois scan architecture you can also embed partial scan business to make the problem more interesting and more practical. But anyway, first we have seen scan, then you have seen partial scan, then you have seen how scans be parallelized, and then you have also seen how it can be optimized in terms of number of input pins, as well as you should not have too many input and output pins for your scan. Still you should have parallelism, at the same time you should not make test faults untestable. So taking everything is an optimization problem which can be solved in this manner as a graph coloring problem. So this mapping I have showed you. So this is one way of optimizing the scan, and as I told you that mostly if I talk about DFT, scan actually plays the role of more than 99% of area, or you can say algorithms, or your space complexity, or the main heart of DFT is scan chains. So therefore, lot of research has been devoted to find out how we can optimize scan chains as well as reduce the test application time and do not make any test faults untestable. So the Illinois scan architecture is one of the most happening algorithm or architecture for that, which we have mainly discussed in this lecture, partial scan and Illinois scan. So apart from that, before I finish the lecture, there are different type of other scans also has been proposed. I will not go into them, but you should know the terminologies, which is actually called the boundary scan. I will give you an idea. So basically this is a chip. So you can apply all the input output patterns, but only thing is we have found out that the internals of the flops cannot be controlled because they are quite inside the circuit and it is very difficult to control, so we are using scan. But there is something called boundary scan. Say for example there is a big circuit board like you have seen your motherboard. So in this case you see 1, 2, 3, 4, so many processors, so many ICs are there. So these pins basically I can say control. This pin I can control, this pin I can control if this chip is separate as a block. But now say all the chips has been put in your motherboard and some faults develop later. How do you test it? So in that case there is something, because you cannot put this chip out and test it. You cannot do that. So rather now you think there is something called a boundary scan, concept of boundary scan, which is called IEEE 1149.1 standard, in which case all the input pins of all the chips are also having a boundary scan. So what is a boundary scan? It is similar to a normal scan architecture, but in fact this is talking about the chips and a system board. In the board you have put all the chips. Now say I want to access this. It is very easy to access if this chip can be brought out and put into the tester. But once it has been fabricated, tested and put in a board, after that some problem happens. How do you detect it? So how do you control it? So there is a scan chain. So that is called boundary scan. So whatever values you have to put, you have to pass by this and the value will be applied. So this is similar to, now instead of a single circuit, the whole concept is a board. So instead of a flip-flop, the circuit has become your flop. So this is a board and these are your chips. So there is this concept of scan chain is called a boundary scan. It is very synonymous to what we know about a normal scan chain. So if this is not a board but an IC, and then therefore you can think this point as a flip-flop. You can only control it from, but you cannot directly control. So basically use a scan chain. But when this same thing is mapped to a board and a lot of ICs are there, we actually call it as a boundary scan, and we call 1149.1. Just the terminologies, we are not going into the depth, but because for the sake of completeness, whenever we talk about scan and DFT, these are very important standards. So just I am just telling you the names. There is some recent ones have come out which is called 1149.4. So in this case what happens? So in this case is a digital circuit. So you do not require any kind of analog pins. But if there is something called pins like a ADC is there, so all those testing of analog components are there. So there is something called analog pins. So analog test pins. So if there is some analog, it has some analog compatibility. So that scan architecture is called 1149.4 architecture. So these are some terminologies. So therefore it will also have some analog components to be tested. So then after that there is some standard called P1500 and so forth. So this scan architecture is also continuing not only in the chip level but also in the board level. So basically with this come to the end of this lecture, in which we have talked about mainly optimization of DFT circuits in terms of scan chip, mainly looking at partial scan and in-line scan. That is what is the core idea, and next lecture we are going to see some more concepts on your test optimization. Thank you.